And I'm just delighted to be here and visit with many people and have coffee and meals and all of that and talk about different aspects of physics, of theory. So for me, this is a big treat. So Giorgio asked me not to talk about mu on G minus 2 per se, but instead to give a talk on the status of lattice QCD as it is relevant to high energy physics. At least that's how I understood my charge. And as I was preparing this talk, and my talk will be impressionistic. It is a colloquium. It is going to be short on technical details and give broad overviews. But I hope to give you enough of an impression to give you enough detail for you to see where we are in the field. But doing that for all of the ways in which lattice QCD and QCD is relevant in high energy physics would actually be too much. So I'm focusing mostly on flavor physics, which is also what my own expertise is. And so here is an outline, a guide to my talk. I start with an introduction to the standard model of particle physics, this being a colloquium that should be accessible to undergraduate students as well. I will start with this and a brief, my own list of open questions. I will talk about QCD and its role in flavor physics, focus on some particular properties of QCD, and then introduce lattice QCD and provide some select results in flavor physics, including also at the end a discussion of mu on G minus 2 and provide you with an outlook. So we start with the standard model of particle physics, which saw completion in 2012 with the discovery of the Higgs boson, long anticipated at CERN. And so here we have a famous picture that probably, even if you're not in particle physics, you've seen many times. The standard model content, the matter particles, the quarks, which are the strongly interacting particles, also weakly and electromagnetically, the leptons, charged and neutral, and then the carriers of the interactions, the weak carriers, the photon, and the carriers of the strong interactions, the gluons, and permeating all of that, the Higgs boson, which breaks electroweak symmetry, or the field breaks electroweak symmetry and provides masses to everybody. And nowadays, a modern phrase of where do all of these the three generations, the first generation being the matter particles that we're made out of, where did the rest of the generation come from, who ordered these, is now phrased that why do we have 3 generations, why not fewer, why not more. Rabi's famous question, by the way, of who ordered that was an outburst of exasperation after discovering that the particle that had been identified for quite a few years as the pion, the mediator of the strong force, was actually a particle called the muon, now that nobody ordered, that nobody anticipated, that wasn't needed. And so that led to the who ordered that. So to me, the muon is always holding a special place. It's the first particle that was discovered that didn't need to be there. There was no theoretical motivation for it whatsoever, and at that time at least. So the standard model leaves many questions open. I think you all know dark matter, dark energy. Why do we exist? How do we exist? Why is there so much more matter than antimatter in the universe, etc. And when trying to form answers to these questions, generically, any theory that goes beyond the standard model generically gives rise then to new particles and to new forces that we might then see in our experiments, and haven't so far. In flavor physics, there's the 3 generations question. There's the origins of the fermion masses. Is it really Higgs-Yukawa? Is it the same for quarks and neutrinos? That seems like a stretch. Are there other sources of CP violation other than in the quark sector? We will find answers to that also very soon. In the neutrino sector, the strong CP problem, which is basically saying that we already know from measurements like neutron EDM that the otherwise allowed CP angle in QCD is very, very small. And we already know from lattice QCD constraints that the quark masses are all non-zero. So there has to be a cancellation that is not understood, or otherwise really fine-tuned. That's known as the strong CP problem, and many other things that we could ask in the flavor sector. So one feature of flavor is that the quark flavor violations exist in the standard model. This just means that different quark flavors, like up and down quarks, can transition into one another via the weak interactions. So these are mediated by charged W bosons, and then all of these couplings are described by what is known as the CKM matrix, the Kabibo-Kobayashi-Maskawa matrix. This is a unitary matrix, so that means that there are lots of testable relations amongst the matrix elements, and that's a very active area. And it has a distinct hierarchy, the matrix itself, and what is the origin of this hierarchy, and is it connected to the fermion mass generation hierarchy observed? In particular, it is striking that the mixing matrix in neutrino mixing has a very different hierarchy, no hierarchy, in fact. In the standard model, we don't have charged lepton flavor changing decays. So this then is a good test for discovering physics beyond the standard model, searching for processes where lepton flavor changes, for example. Lepton flavor universality allows us another way to put cracks into the standard model, and you'll see examples of both later on. So I'm mostly focused here on what are known as indirect searches for new physics. In order to find answers to these questions, finding evidence for particles that are not in the standard model can then give us hints as to how to build the theory that goes beyond the standard model. And one looks for processes that are forbidden in the standard model, such as proton decay, lepton flavor violating decays, as shown here, and other examples where an observation would provide us directly with the discovery of new physics. However, to interpret the discovery of new physics, we also need to understand how strong interactions affect these processes. In studies of rare processes, meaning that they're loop suppressed in the standard model, so in the standard model the rates are small compared to tree level processes such as neutral meson mixing, flavor changing neutral current decays, and the muon magnetic moment, for example. One can compare theory against experiment and look and perform precision tests here. In checking lepton flavor universality, one can also look for deviations over standard model expectations, or, as I already said, overdetermine the standard model parameters, in particular the quark W boson couplings, by testing various aspects of unitarity of the CKM matrix. So a common theme in all of these then is that we want to obtain information on short distance physics, maybe a new particle or dark matter particle that lurks behind an observation, or we want to use the experimental measurements together with theory to obtain precision determinations of the fundamental parameters of the standard model, and then learn more and over-constrain it. In many cases, this information is hidden by hadronic or nuclear effects that must be accounted for by theory, and generically these are nonperturbative QCD quantum chromodynamics effects. So we'll talk about that a little bit more, but in principle this points to a need for having computational tools that allow us to precisely calculate these effects, and as I will show you later on, lattice QCD is one such tool that allows this. So let's talk, again in the colloquium framework, let's talk a little bit more about QCD. We have the feature of quark confinement, which means that quarks are always in bound states. This can be explained in quantum chromodynamics via the generation of a potential between two color sources that creates a linear flux tube, which results in confinement and or breaking of the flux tube instead of allowing the quarks to simply separate as they would in the presence of if they were interacting via a dipole field, for example. Okay, so confinement, linear rising potential, flux tube, all known features of QCD, and in fact that was one of the early success stories of lattice QCD calculations, is to show that the potential is indeed linearly rising with ever more realistic calculations. So if we take a look inside one of the most ubiquitous particles, the proton, in the quark model view of the proton, and you've seen this in textbooks in kindergarten and undergraduate physics, you have the proton consists of 3 quarks, 2 up quarks and a down quark. They have the 3 colors sum up to be colorless. The 3 quarks, their spins sum up to spin 1/2 exactly, and then they're bound together by glue, and that's what the proton looks like. And that is completely wrong, even though the quark model does provide a good description of the degrees of freedom of the proton at its spin 1/2, etc. The actual QCD view of the proton is as a strongly interacting many-body bound state, which is, of course, a theoretical problem that is difficult to solve, and this is where lattice field theory comes in. The structure of the proton is really fascinating, and we're still understanding it both experimentally and theoretically better and better. And there are, in fact, a new class of lattice calculations that are being developed to provide a more detailed understanding of proton structure, including spin and transverse momentum distributions. I'm not going to talk about that at all here. So another interesting feature of QCD is the very different binding energies, if you want to call it that. So the sum of the quark masses is much less than the actual mass of the proton. This is, of course, well known. So this means that the effect of the Higgs boson on the proton's mass appears to be quite small. And in a very real sense, we can say that, most of our mass is actual binding energy, is QCD effects. And again, understanding exactly all the contributions is still a question of ongoing research. So all of these oops, this was unintended. That's interesting. I pressed the same button. Yeah, so let me see. Okay. The well-known particle zoo, the QCD spectrum consists of bound states. Those can be fermions. Fermions are called baryons, or bosons, which are called mesons, and there's a rich spectrum. And via the flavor-changing weak interactions, there's a rich phenomenology. So starting with the famous nuclear beta decay, where if you look inside, then you have a neutron inside the nucleus decaying into a proton, and looking inside there, then there is a quark flavor-changing interaction mediated by a W boson and controlled by the CKM matrix element VUD. And a particle physics equivalent of this, so the equivalent processes to nuclear beta decay are meson level beta decays, where a B-flavored meson decays into a pion or a D-meson, again under weak decay, controlled by the corresponding CKM parameter. Here we have a B quark transitioning to a charm quark, and then a virtual W boson that decays into leptons. So this is a beta decay as well, or here I've drawn it for muons, not electrons, but it's the same principle. These are called semi-leptonic decays, semi being half the final state is leptons, and then you also still have a hadron in the final state. So there are many other decay processes of mesons and baryons that are mediated by the weak interaction. This is, as I said, a very rich field with many different experimental measurements, and hence a lot to calculate. So finally, what I also want to talk about is another very crucial feature of QCD is called asymptotic freedom. And let me start this discussion by talking about the QED coupling, which increases with energy. And you might question the scaling in this plot here, which is showing that the QED coupling, so it's not a constant, it runs, it goes from 0 energies, where it is 1 over 137 to about 1 over 128. So that's a steep increase that you can clearly see here. And of course, I'm going to compare that to what happens in QCD. So this running of the coupling can be understood in terms of charge screening, that if you put an electric charge in a dielectric medium, then the charge gets successively more screened as you go further away from it. And this is relevant because the vacuum is a dielectric medium, as in the vacuum you can have virtual photons that fluctuate into charged particles, electrons, quarks, and any other charged particles for an instant, and they can of course be diagrams on higher and higher orders that you can also include in order to compute the running of the coupling. So in QED, the coupling becomes stronger as you go to shorter distances or higher energies. And in QCD, you have the same effect. You also have a vacuum polarization where gluons split into quark-antiquark pairs. But in addition, which results in charge screening, but in addition, we have these interactions between the gluons, and which result in anti-screening and very famous Nobel Prize for the discovery of asymptotic freedom. And that then schematically looks like this. So the running of the coupling asymptotic freedom then also self-generates a scale which corresponds to the gluon and light particles energies inside hadrons, called lambda QCD. We don't have to work with a sketch by itself. We can look at the evolution of the coupling as measured in experiments and confronted with perturbative QCD predictions. So QCD tells us how the coupling evolves, and you can see that this has been verified in many different experiments and series of experiments that the coupling really does obey asymptotic freedom as predicted. By the way, the running of the coupling can also be computed non-perturbatively and agrees very well with the with perturbative QCD. In lattice QCD, there have been some beautiful calculations of this. Okay, so what does asymptotic freedom? I mean, it's obviously a crucial feature of QCD, and it means that we can perform perturbative calculations at high energies, and that's very good for high energy physics, for phenomenology, and has given us lots of quantitative information about QCD, and it means that at low energies we need to result to non-perturbative methods. Perturbation theory simply doesn't make sense. Now, the generation of an energy scale, lambda QCD, also plays a role in the flavor symmetries of QCD, where we now have 3 quarks that are smaller, their masses are smaller than the typical energy scale than lambda QCD, and 3 quarks that our masses are much larger, or successively much larger than lambda QCD. And so this allows us to understand QCD in terms of flavor symmetries. So chiral symmetry, which we know is spontaneously broken by a chiral condensate, an expectation value of psi bar psi, that becomes non-zero, that breaks the original chiral symmetry, global symmetry of the QCD Lagrangian to the flavor symmetries. And the addition of small quark masses, then in addition to the chiral symmetry breaking, we have explicit symmetry breaking by the small quark masses, and this allows us to in the low energy regime to describe QCD in terms of chiral perturbation theory. So if we only look at up and down quarks, that is described in terms of isospin symmetry, and the reason discovered long ago for why the neutron and the proton masses are so similar in the context of including the strange quark, which is of course not really degenerate. In the degenerate limit, this is SU3 flavor, which is then of course broken, but is a useful way to catalog the spectroscopy, and also provides, via chiral perturbation theory, useful constraints and a useful description of low energy kaon experiments, for example. And it also is very useful for understanding QCD and lattice QCD in that region. On the other side, when the quarks are much heavier than lambda QCD, we can think of a heavy quark expansion where 1 over the quark mass goes to 0. And while the top quark is certainly absurdly heavy, it also decays weakly very quickly and doesn't form bound states, and we're interested in bound states, so this really applies to bottom and charm quarks. And in the limit where the quarks are all very, very heavy, much larger than lambda QCD, we have a heavy quark symmetry, and there's also a spin symmetry that comes along with that. And out of this, one has developed the heavy quark effective theory. So another effective field theory that describes and provides some simplifications to QCD in these limits that one can then move away from in a power series expansion. Okay, so those are the flavor symmetries that will play a role when I talk about lattice QCD. So let me introduce what lattice QCD is, and that discussion starts by going back to by going back to Feynman's path integral, which provides us with a different point of view in describing quantum mechanics So in Feynman's path integral, a transition amplitude is described by summing over all possible paths, which is then formalized by this functional integral, which is actually defined by, in 1D quantum mechanics, taking a time lattice with a fixed lattice spacing and then taking that time lattice spacing back to 0. So starting with a finite countable, or finite if you consider a finite time extent, integral, high dimensional integral, but still finite degrees of freedom, that then becomes infinite in the limit of taking the lattice spacing to 0. So if we think about this, then if one is computationally inclined, one thinks immediately that this is something with a finite time extent that can be computed numerically as long as n is finite. And then there are efficient numerical computation strategies such as Monte Carlo integration that allow this, but not when you have something that looks like a fluctuating phase. That gives us a numerical integration problem that is not well conditioned, that would not be amenable to numerical integration. So one can instead go to Euclidean time, which will then turn this into something like a Boltzmann factor. So lattice QCD is defined entirely then in Euclidean space. So now it's conceptually at least relatively easy to go from path integrals in quantum mechanics to path integrals in quantum field theory. So instead of a path x of t, we have quantum fields that depend upon the four-dimensional space-time. And so instead of a time lattice, we have a four-dimensional space-time lattice. And I'm not very good about drawing multi-dimensional lattices, so we are stuck with 2 dimensions here. I'm not even going to try 3 dimensions. What's the point? So instead of the functional path integral here, we have a functional field integral over field configurations. When we have n time lattice points, then this integral has n dimensions times any other internal degrees of freedom. Here we have n to the 4 dimensions times additional internal degrees of freedom, which of course we have when we talk about something like QCD, where we have spin, color, etc. Okay, so that's in a nutshell what lattice field theory is. And lattice QCD then, of course, starts with the QCD Lagrangian, and derivatives need to be discretized, so derivatives become difference operators. The gauge fields in Wilson's formulation of the lattice field theory are treated as link variables, and that allows us to maintain gauge invariance even at finite lattice spacing. That was one of the things that Wilson, who invented lattice gauge theory, set up right from the start. So we don't have to wait to recover gauge invariance until we take the continuum limit. Gauge invariance is manifest, but of course other symmetries are not. Because now we have broken rotational invariance, for example, and those are recovered in the continuum limit. Okay, so long story short, when we think about putting the system on a computer, then in addition to discretizing space-time, which is one approximation or several approximations that we make, and how well that approximation works depends on how hard we work here. Other approximations then is putting the system into a finite spatial volume and a finite time extent in order to be able to compute the resulting integrals on a computer numerically, we need to have a finite number of degrees of freedom. So these are all approximations that we need to take away. I'm not going to talk at all about how to do these integrals. That's swept completely under the rug in this talk. other than to say that these integrals can be evaluated using importance sampling and Monte Carlo methods. And there's a long history of developing these methods. And the most important point to know from this is that the Monte Carlo integration introduces statistical errors into the calculation. So much like an experimental measurement, a lattice calculation has to deal with both statistical errors and systematic errors. And we talk about generating data, meaning lattice data, and we talk about increasing our statistics, which is basically saying that we're integrating harder, we're generating more gauge field configurations over which we put into the integral, and that's how we increase our statistics. The language becomes very similar to language used by experimentalists who increase their statistics by extending their runs or making the beams more intense, etc. Here we increase our statistics by calculating harder or longer or on bigger computers, doing the same thing harder and longer. So in principle, statistical errors are as large or as small as how much computing power you throw at the problem. It's not always quite like that, because sometimes your statistical errors grow for known reasons, and one has to work a little bit smarter, not just harder. Okay, now these are approximations, and what we really want is not know about the results of a lattice calculation with these approximations in them. What we want to know is what these calculations have to tell us about the real world, which is in the continuum. As far as we know, we live in a continuum, which is in an infinite volume and in an infinite time extent. So we need to take these approximations away, but these approximations all come with adjustable parameters, so we can take them away. We can perform the computations at more than one lattice spacing and take the lattice spacing dependence away that way. By the way, the lattice spacing is not a parameter that one sets, it's a parameter that one measures. The parameter that is set that determines the lattice spacing by asymptotic freedom, by this property of QCD, is set by the coupling. So by setting the coupling, we obtain a certain lattice spacing that we need to determine by comparing physical quantities computed on the lattice with an experimentally measured quantity. So there's one physical quantity that is used to tell us what a given gauge coupling, what scale a given gauge coupling, what physical scale a given gauge coupling corresponds to. That is not something that is within the theory. The other parameters that QCD itself has nothing to say, that QCD itself doesn't predict, in addition to the gauge coupling, which is hidden here and hidden in the covariant derivative, are the quark masses. So in our lattice experiment, we can adjust the quark masses freely. Of course, in the real world, the quark masses have the values that they have by giving us the hadron masses that they have. So we can adjust the quark masses by computing hadron masses from them and then comparing those to experimentally measured masses and adjust things until the experimentally measured hadron masses agree with the masses computed in lattice QCD. So that's then another set of parameters, one for each quark mass that you have to, that is not a prediction, that we don't predict, we're using as an input. But that's always the case because the parameters of QCD can only be determined experimentally. Here they're determined experimentally from hadronic quantities. Okay, so as I said, these adjustable parameters can be varied. We can vary the lattice spacing by varying the gauge coupling, and we can then perform the same computation at an increasing set of finer lattices with more and more points if we have the computational resources to do that, and then look for lattice spacing dependence. So we want to do the same thing with the volumes, and then we also want to be able to adjust the masses, because your first guess of what the mass is would probably not be right. You want to do the computation always at several masses until you get to just the right place. In the olden days, we were not able to perform the calculation at the physical up and down quark masses. That was just the limitation of both the methods and the available computational resources. But that's the bad old days. In the good new days, adjusting this to their physical values is no longer a problem. But what this means then is that a lattice calculation is never a lattice calculation that is providing a prediction of QCD effects and to be compared with experiment is never a single computation, but it is a series of calculations on different ensembles where you vary the lattice spacing. Here you can see on the bottom here is lattice spacing squared, because I'll talk about discretization effects in a minute, and the continuum limit is going to the left. The cyan star is the physical point where the pions have their physical mass. And you can see that it is advantageous for us to include ensembles where the pion masses are unphysically heavy. That allows us, as I will discuss a little bit, to use chiral perturbation theory to control the mass dependence. We also have different volumes, and it is interesting to study things like the SU3 limit, so having strange masses that are not at their physical masses. So this notation here, which you will see in many lattice papers or something like it, means that these are configurations that have quark flavors in the C, where the 2 corresponds to a degenerate up and down, two degenerate up and down quarks. The first one corresponds to a strange quark at its physical value, and the second one, or unphysical value, and the second one corresponds to a charm quark. So that's a complete and realistic description of the QCD-C, as isospin breaking effects are generally smaller than the precision that we need in most cases, but not all. Okay, so in order to get to the physical point, we must have a lattice calculation must be based on a multi-ensemble analysis, as shown here. If you are wanting to judge whether a particular result can be trusted, the first thing to look for is a table that lists ensemble parameters and talks about the range of lattice spacings that is covered and the range of other parameters that are covered in the computation. Okay, but we still need guidance for how to extrapolate or interpolate to the physical point or physical points, and this is part of the systematic error analysis, and this is where the effective field theory description provided by the flavor symmetries becomes important, and other effective field theory descriptions also become important. So long ago, Szymanczyk developed an effective field theory description that allows us to describe discretization effects. Again, it's using separation of scales, of hadronic scales and short distance scales, and allows us to describe discretization effects in terms of a effective field theory in a series of continuum operators and continuum states. And so this gives us theoretical guidance to the continuum limit. Chiral perturbation theory provides us with guidance to now interpolating to the physical point. Heavy quark effective field theory provides us with guidance for discretization errors, effects associated with heavy quarks, and also if there need to be adjustments. And there's a series of papers that started with Lucia on how to understand the infrared effects of finite time and finite volume that I will not talk about, but again, there is theoretical guidance about them. In particular, for the kinds of simple systems that I talk about here, finite volume effects generally fall off exponentially if you are in a large enough volume. Okay, so the effective field theory description really underpins the systematic error analyses that are done and provide us then with an ab initio, no assumptions made other than properties of QCD in the calculation. Let me just go into a little bit more detail on discretization effects. That's obviously always important. So from semantic EFT, we obtain relations like this, where for a given observable computed in lattice QCD is related to the continuum quantity times plus lattice discretization artifacts that generically go like a positive power of the lattice spacing, provided that we are in this regime. And then there might be a power series expansion. There can be logarithmic corrections to this depending on the exact way in which the action is discretized. This provides us with a functional form, also provides us with the tools to build improved lattice actions and anticipate the size of discretization effects. So it is very important. So using this together with this then gives us control over discretization effects if done correctly. Okay, just a very quick introduction into the different ways of dealing with the quark action. So without going into detail here, there's a famous Fermion doubling problem, which you can see if you just start by taking the derivative and writing it as a discrete difference and looking in momentum space, where then momentum turns into a sign of the momentum, and you have doublers at the Brion zones. The Fermion doubling problem is connected to chiral symmetry in QCD, and there's a very famous no-go theorem that tells us that you can remove the doublers and have an ultra-local Dirac operator and but at the cost of losing chiral symmetry, you can keep the doublers and keep some remnant of chiral symmetry, or as was discovered in the form of Ginzburg-Wilson fermions, you can remove the condition of ultra-locality and just have a local Dirac operator, so it is now larger in some sense, and have chiral symmetry that is broken still, but chiral symmetry violations are now exponentially suppressed. Okay, this is autocorrect going crazy. Okay, so these then inform the three main strategies that are used in most large-scale computations, starting with staggered quarks, which of course, which have a very famous alternate name that is familiar to all of you, where the strategy is to reduce the number of doublers by staggering the fields, but it still keeps some of these unphysical doublers. They're now called tastes to distinguish them from quark flavor. The dominant discretization effects in this framework are then due to taste breaking effects, which however can be corrected analytically, also via chiral perturbation theory. Generically, these actions have discretization effects that start at order a squared, and with some improvement, the a squared terms can be highly suppressed. In particular, improved versions, which involve some smearing and other adjustment of operators, can reduce taste breaking effects and greatly reduce discretization effects. The best of these staggered actions is called HISC, highly improved staggered action, which is what my collaboration is using. So all of these introduce some complications into the formalism, but what is attractive about this Fermion framework is that it is computationally inexpensive. It is desirable to, when doing lattice calculations, to have this done by different groups, using different discretizations, and then seeing that in the continuum limit, we recover universality. There's one continuum limit, there's one QCD. At finite lattice spacings, all of these different computations give you different results, but they all agree in the continuum limit. That's a very powerful way of testing, internally testing lattice QCD calculations, because it's not just the principle, it's also the practice and how the systematic errors are analyzed. Again, this is very similar to an experiment where you also want to have more than one experimental analyses in order to make sure that everybody has dotted their I's. Okay, so let me now explain where the title Finding Beauty comes from. When people started looking at how to deal with beauty quarks, bottom quarks, in a lattice calculation, this was back in the early days when lattice spacings, and this is still true in many cases, when lattice spacings were so large that the Compton wavelength of a B quark would be smaller than the lattice spacing, and people used to say something like, well, the quarks are just falling through the lattice, you can't treat them that way. And that's actually not quite true, because we're not dealing with quarks, we're dealing with bound states, mesons. And a B meson, for example, that consists of a B quark and light quarks is an extended object that sizes of order lambda QCD. It is most definitely not falling through any lattice. And the B quark that, as you take its mass larger and larger, just becomes a color electric source, also known as a Wilson line. So that's the limit, infinite mass limit of a heavy quark effective theory. So we can certainly treat systems that have B mesons in them if we use an effective field theory approach in the situation when the B quark mass is larger than the ultraviolet cutoff provided by the lattice spacing. So that means that B quarks require a different treatment, a different way of discretizing them compared to light quarks. And that was true for many years. And the community figured out how to do that profitably using an effective field theory such as HQET, heavy quark effective theory, or non-relativistic QCD, which is of course the equivalent of non-relativistic QED, where B quarks will have a finite velocity, and it's a velocity expansion. So start with the EFT, discretize those, and then of course the continuum limit becomes much more complicated, and in fact matching and renormalization also become much more complicated. In principle, you can carry this program through. You can also carry this program through using nonperturbative methods, but that becomes also really, really difficult to do. So in practice, these difficulties mean that practical computations, practical calculations are limited in accuracy by how well practically you can work out the renormalizations. Basically, the actions and discretizations are really complicated enough, and there are too many terms to just do this in an easy, non-perturbative way, and perturbation theory also becomes hard. Okay, another approach was developed at Fermilab, so I was part of that, where we start with a relativistic action like the Wilson action, and then match that action via heavy quark effective theory to the continuum. So this has a well-defined continuum limit, but still the problem of non-trivial matching and renormalization. But we have used this formulation profitably to obtain actual precision results that are pushing towards 1% precision via some clever ways of doing some of the renormalization, at least non-perturbatively. Okay, now with the development of more improved actions, highly improved light quark actions, and Moore's law providing us with more computational resources, allowing us to generate gauge field ensembles where the ultraviolet cutoff is now larger than the B quark mass, we can basically come full circle here. We can now employ a framework where we can use the same action for all quarks, where the renormalization is now very simple. And so the setup is simple and beautiful. So here we're finding beauty in both the setup, and we're finding beauty because we can resolve B quarks now with small discretization errors. This is now small if you have a quark discretization that is improved enough. And so all of this beauty then allows us to do these calculations at exquisite sub-percent precision, even for B physics quantities, not just light quark quantities. Okay, let me see. How far along am I? How long did I talk about?
5 minutes.
5 minutes, oh my goodness. Okay, the state of the art now, so anticipating the examples that I will show you, is that we now have lattice QCD calculations of simple quantities, where a simple quantity is mostly mesons, but also baryons that are stable. So stable under the strong interactions. You have at most one in the initial final state. You might have none. This is where we understand finite volume effects very easily. And for such simple system, we can perform calculations where we can quantitatively account for all systematic effects with exquisite precision, reaching sub-percent precision, and in some cases, total errors that are commensurate or even smaller than the corresponding experimental uncertainties that enter into, say, determinations of CKM matrix elements or comparisons of theory against experiment. At the same time, we see a vast increase in the scope of lattice calculations, lattice QCD calculations of quantities that were not supposed to be part of the program, that were supposed to be out of reach of lattice calculations, including QED effects, including resonances and scattering, and other structure-dependent long-distance effects, inclusive decay rates, etc. Methods are all being developed for these non-simple quantities. And this is exploding, and there's a lot of very interesting work on structure functions, PDFs and GPDs, and related quantities. Okay, I think I've already made this point that we have a rich program of experimental measurements of weak decay processes, decay rates, differential decay rates, that on the standard model side, the non-perturbative effects are then parameterized in terms of hadronic matrix elements, which we then need to compute in lattice QCD. And we can either take the lattice QCD calculations and compare them to experiment to then determine standard model parameters. This is hadron masses to quark masses. This is CKM matrix elements from weak decays, etc. Or we can take the lattice calculations and put them into the standard model into the standard model expressions and compare standard model theory with experiment and look for tensions. Okay, I'm going to skip this and this and this. So here's the state of the art for kaon physics for leptonic decays and semi-leptonic decays involving kaons. And this is a very busy plot. What this shows is called a flag plot. FLAG stands for flavor lattice averaging group. They've been taking the world's lattice calculations, evaluating them, and then performing average. That's a very good service to the field. And so you can see, first of all, the consistency of results for the ratio of kaon to pion decay constants, and the overall precision at sub 0.5%, also for the KL3 form factor, all made possible up here are the most modern calculations by having ensembles with physical light quark masses with improved actions, and then because the C and the valence quarks are all the same, employing Ward identities and other no renormalization theorems, so that one doesn't have to deal with matching errors. This precision then allows us to perform very precise tests, for example, of the first row of CKM unitarity, and we're now seeing some tensions with first row CKM unitarity, which is a bit of a surprise, and it has revealed that the extraction of VUD from nuclear beta decay needed to be refined, that structure-dependent corrections also in the electroweak corrections needed to be quantified better. They had not been, and doing that then reduces the tension, but there's still tensions here. This is still a story that's not finished, and it will be interesting to see where it goes. It's a surprising place to see deviations from the standard model, but it is, as I said, it is not finished, and of course 2 standard deviations and even 3 standard deviations is not enough to claim discovery, and one needs to understand some of those electromagnetic and structure-dependent electromagnetic corrections better. Okay, I promised you for B mesons also sub% precision, and here you can see the overview of decay constant results. So this is where B meson decays leptonically, either via a charge W boson, or a neutral B meson could decay leptonically via flavor-changing neutral current process. The hadronic matrix element is essentially the same. And so here you see these results. These are the most precise results come from our collaboration, which are based exactly on the finding beauty calculation that I outlined, having a large set of ensembles with a large range of lattice spacings, with the finest lattice spacings being small enough so that you breach the B quark mass barrier over here. And using the highly improved staggered quark action, you can see that even at very large masses, discretization effects, which are the deviations of the colored lines from the continuum cyan line, which provides us with the decay constant as a function of heavy meson mass, are very, very small. So that's somewhat by design of how this action was developed. Okay, so as a result, then, when we take the lattice calculation of the decay constant and put that into the standard model prediction for the rare decay where a B sub S meson decays via flavor-changing neutral current into a pair of charged leptons, in this case charged muons, and so if we put that in there and then look at the sources of uncertainty in this number, the decay constant is third down the row. So basically the QCD, pure QCD effect is done. Other things need to be improved. Also lattice calculations that feed into the parametric uncertainties due to CKM matrix elements and structure-dependent electromagnetic effects, which can also be at some point, may also be at some point, be done in lattice QCD. Okay, I wanted to show this plot. This is a cherry-picked selection of so-called flavor anomalies, where this anomaly is an anomaly that comes from comparison between the standard model and experiment showing some tensions. The largest of the current flavor anomalies is the muon G-2, where you heard a talk on the experimental measurement. In general, as is expected, the common source of theory are QCD effects. So that's reducing these here, and ongoing experimental measurements will reduce the blue bars. I'm going to skip this. This is just giving a shout out to the first calculation, lattice QCD calculation of the form factors for this process at non-zero recoil, which provides a refined calculation of the flavor, lepton flavor universality testing ratio here, which made a big splash some 10 years ago when Babar discovered that this was rather far away from standard model expectations, but now we have refined standard model calculations, and this recent result actually increases the significance of the tension back to close to 4 standard deviations. So it's becoming serious again. These successive experiments had reduced the tension, but now we're at a larger tension again. For muon G-2, you saw this plot from Dave Herzog's talk, just to point out that in the standard model, the anomalous magnetic moment receives contributions from QED. Those are known to a precision that will not be challenged for 50 years by experiment. Same for weak contributions. And the standard model prediction, the uncertainty is entirely driven by the hadronic corrections in the form of the hadronic vacuum polarization and the hadronic light by light, where, as Giorgio mentioned, I'm part of the muon G-2 theory initiative, which is not actually organized by Fermilab. It's self-organized. Fermilab supports us and likes what we're doing, which has recently put out a white paper summarizing the state of the art. And you can see that for lattice calculations, we are in a confused state and we have a lot more work to do. This is just my summary. It's just saying that we have a large menu of lattice QCD results that you might call flagship results, and a large menu of new results, of new calculations, new quantities that people are developing, and some of these might be in the flagship results very soon, and in particular, maybe at some point something's going to break. And the importance of refining the QCD uncertainties using lattice QCD to really test the standard model in light of continuing also experimental efforts, including for mu on G minus 2. It just highlights the discovery potential of this effort, and hopefully will lead to discovery, or at least to very, very tight constraints on possible new physics. Thank you.